Welcome back. Oh, you're still muted, Sandra. Oh. Hey, Pam. Are you back in Indiana, bro?
Yeah, it's been a hard week.
Oh yeah, I can imagine.
Oh, are you sick? You sound sick.
Yeah. Yeah, so let's see. Had shoulder surgery on Tuesday, COVID on Wednesday.
Ouch.
And then kind of drug interaction issues.
Oh,
Um,
yeah, well, that's no fun at all.
but no, I really appreciate your being there last weekend.
Yeah, that was a very amazingly good event. So I was very impressed with the, for what was it, 100 people on a Zoom call?
Something like that, yeah.
Amazing.
Yeah, this is a
Sorry.
memorial service for my brother.
Yeah, David mentioned. Very sorry for your loss.
Yeah,
I wish you could have met him.
yeah, really
He's a
cool
good
guy.
man.
Yeah.
You met him, David, before?
Oh, I've known him for decades. Yeah,
Okay.
long time. Yeah.
Okay, cool.
So, no, I was really dignified. It was, so I think it's the Quaker thing where you have 100 people on a Zoom call and everyone's silent. And then somebody will speak for a minute or two. And then everyone goes silent again. And then somebody else. Like it's not, it's very, very, very good. So no, I was very impressed with that whole thing. So that was good. Yeah, I had a fascinating week. I have been completely perplexed by multi-head attention. That has been dominating my worldview the last week. I spent a lot of time coding different attention models and multi-headed attention and stuff. And I've come to the conclusion that you could use multi-head attention to do multi-agent simulation. So I think that multi-head attention would be a really powerful way of modeling economic systems.
So what's the intuition with a multi-head attention? I mean, how's it work?
So Payam, why don't you give your intuition first and I'll give mine.
Well, I mean, I guess that if you understand what attention is, like you try to basically map one sequence to another or to itself in terms of self-attention, right? Like you look at the weighting between different sequences. I think multi-headed just means you have different versions of that. So you can just have multiple different weightings that are learning different things about the mapping from one to the other. At least that's my very naive understanding. So it's like nothing qualitatively or qualitatively different. It's just more, you can learn different functions between two sequences, basically.
So to say exactly the same thing slightly differently, you could have, they all receive the same input, so they all have access to the same information, but they have slightly different preferences, right? So each attention head, like one attention head might focus on a particular word or concept, and another attention head might focus on a different word or concept. And
I mean, another way to think about it is also its scale, right? Like in terms of images, like each attention head could focus on something interesting at different scales.
Sure. Yeah.
So like in an image, one might, I don't know.
When you look at texture, it would be like one attention head, and then you look at maybe what are objects, it could be another one, and you could learn these in parallel with the same image because all the information is there. It's just the fact that you separate it to different heads to focus on it. I guess you get better results. But I think, David, you've been doing research recently. This is like the extent of my knowledge. I've never used them. I don't know beyond what I just said.
No. Yeah. So I'm not disagreeing with the word you're saying. So the way I think about it is that you can hold a conversation and drive a car at the same time because there are different systems attending to driving the car versus talking, right? So you're not a single-threaded machine, if you will. We are very heavily parallelized. And this parallelization manifests itself in the form of these different attending mechanisms that have different preferences, right? They have different interests or different reward functions. So if you think of an economic system and you think of each agent as an attention head, then you have a system where you have a bunch of different attention heads interacting. Those attention heads are all getting the same information, but they have different preferences, and they are all affecting the output, right? So every attention head is having a say in what the output should be. And sounds like economics to me, right? You have a bunch of people in an economy and they all have individual preferences. They all have access to the same information.
It also sounds like neuroscience, no? Like, you know more about it. It feels like our brains are full of these attention heads and they vote, and depending on what kind of day it is, one group wins versus another, right?
Exactly. And that's what I've been working on with Bernard, my other professor friend. And so we've been looking at walking in virtual reality, which involves many attention heads. And he actually has he's done explicit experimentation on this, where we have these different ways of moving in VR, and they basically, we attend to them differently. Some of them make us sick, others don't. Some of them are very compelling, some of them are very awkward. But I have also been trying to work with the data that Rob gave us, and I'm trying to come up with a way of producing a multi-head attention model that can work on time series data, and I'm not there yet. I think it can be done. My understanding is that attention heads do work with sequential data, so it should work. I just lack the understanding or have not found a good example where I could actually just do this.
Yeah, one example I was wondering about is if you have sort of different forecast horizons. So maybe 1 period ahead versus 2 period ahead.
Yeah, that goes back to the whole scale, right? I guess in time scale you're talking about, I was talking about spatial scale, but yeah, it's the same idea. I think it totally makes sense to do that.
Yeah, so you would have different attention heads. And I think if we really picked apart economic theory, you could actually express a lot of the equations and a lot of the techniques in this manner. That's all. Yeah, so I find it just super interesting. So that was it, really. That was my kind of week. I
guess it goes back to, like, I guess the challenge is not, I mean, the idea is good, but the challenge is how would you train such a thing? Like, it's not clear to me, because all these transformers, attention networks, they're very, very data hungry, even more so than typical neural network. And you usually need a lot more data. And I don't know where you would get this data in, like, economics or other places. Not to say that it's not possible, I'm just saying that's one of the challenges.
It is. And I think that there's an abundance of data if you reduce your time scale because of high-speed trading. Like, you could tap into a millisecond data stream and have a huge amount of data at that time scale, but I'm not sure if there's any information at that time scale that really has local effects that produce, large scale changes. I don't know.
I would suspect so.
Yeah. And the other thing I was thinking about a bit earlier in the week was I've been once again obsessing about GANs, and of course I'm trying to work out if you can build a multi-head attention GAN. But one of the things I realized, which I thought was useful and I thought I would share, is you can train GANs asymmetrically. So if you have a model that can generate predictions, you can train a discriminator using that as the generator, right? You don't need to train both at once. you can train half and then use the other half that you train to train another half. And so you can essentially have a critic. Like if you've got a model, then you can train a critic. And if the critic, so let's say that I have a model that predicts economic behavior. All right. And I have real world data. And now I can train my critic on saying, is this real world data or is this synthetic? Okay. And
yeah, but there is a problem. I mean, there's a reason they train GANs like the discriminator and generator together. And because one of the failure modes is if one of them overpowers the other one, basically training fails. If the generator gets so good that the discriminator hasn't learned to tell it apart, there's no learning happening, it falls apart, and vice versa. If the discriminator is super good, then whatever generator does, it's gonna it's not gonna get, so that's why like coordinating the generation and discrimination is the way they get GANs to work. So if you have one of them already good, I don't think you can train the other one just from that. Maybe there's other ways of doing it.
I'm not arguing, but as a kind of a scientific test, right? If we're trying to test different economic theories, let's say, if we found, and there's this failure mode, I'm not disagreeing, but we can actually exploit the failure mode, potentially, this is an idea. So if we have a really good one, then that would be, like, let's say I have real world data and 3 different economic models, okay? And I train a discriminator or to detect the difference between the real and each of the individual 3. Each of those will come up with some loss function. So we should be able to come up with some metric of the fitness of those different economic models to model the economic data. And that might even tell us a little bit about which model is likely to be more accurate, potentially. That's kind of my weak argument. It's not a strong argument, and I'm not saying it is. But it just is a way of bootstrapping. So certainly once you've got, if you don't have anything, then you can kind of bootstrap the GAN with a handcrafted model so that the discriminator has some priors, and then you could switch out that with a machine learning generator, which could learn from the priors of the discriminator, and you could basically ratchet your way up. While I guess what I'm trying to get at is curriculum learning, where if we start with an economic model that we understand, and then we kind of ratchet away from that, we might be able to retain much of the original economic model in the ultimate model. It has certainly been tuned with priors, but it hasn't been replaced. That's one idea. The other idea would be to handcraft the latent space itself. So the latent vector really would be the interest rate, I don't know, a bunch of economic factors, and you would just encode those in a vector, and that would be the latent space that the two communicate through, rather than just randomly picking the latent vectors. We might, I don't know if anyone's done this, probably have. Can we essentially handcraft the latent space so that it fits in with our understanding? And that way the model will be able to tell us things that we can essentially interpret from the latent representation. I don't know. These are ideas. I'm sure others have had them, but that's basically what I've been chewing on. So how was your week, Pine? What did you get up to?
It was busy. We were working on a proposal, and I think I mentioned I was given the go ahead to do my little research project a couple of days a week, which I haven't had a couple of days a week to do it yet, but
it always happens that way.
But I've been meeting with some professors and fellows to get their take on what I'm trying to do, and yeah, it's been interesting because I met with this guy yesterday. He's a professor at University of Alberta. I'm not going to mention his name since we're being recorded. But so his specialty is like pathfinding in graphs and like combinatorial optimization. So my idea was I am trying to build a platform that you can configure to basically simulate different logistics supply chain scenarios and then to try different algorithms on it. So the whole time that I had with him, he was basically trying to convince me to use his platform that he's been developing for 17 years in C++. And so he was like giving me demos, and it made me realize that that might be the end I'm going to go towards, even if it's successful, that, you know, when you build a platform, it's not trivial to get people to use it. Because everybody has their own preferences, things they want to do. So maybe just even the idea of going with a new platform, yet another platform that you have to go around, convince people to use it, is a dead end. I don't know. It made me rethink in a way that I didn't expect, that this whole sort of direction of research.
I've fallen in love with Lightning. I think it's amazing. It's just so simple. You define a data loader, you define a training function, you define like 3 functions. You're done.
Yeah,
Sorry, what is it?
PyTorch Lightning is a recent
Okay.
package that was developed that aimed to make building and training and utilizing models as simple as possible.
Yeah, it's kind of like Keras for PyTorch, right? That's sort of what the goal of Keras was for TensorFlow. It's like a wrapper around the original just to make it even easier for people.
And I can also share what I shared with PyM last week, because Rob hasn't seen it. So I'll just walk you through that very quickly as well. One sec. Carry on.
By the way, David, I think I have to take back what I was arguing last week.
What's that?
I think your whole idea of using the autoencoders, I said it's probably not going to be working. I was reading in my other reading group that I go to every other week. So we were reading the stable diffusion paper. So it's like a 40-page paper. So that was part of the reading group. And that's what they did. Like they took some pre-trained autoencoder. I mean, it was for images, not for economic data.
Sure.
But the idea was they still took a bunch of encoders to get the latent space, and then everything was done in the latent space. And that's the whole reason the stable diffusion, which is now freely available, is a lot faster, and you can run it in your local machine compared to Dolly, where you need like GPUs, like lots of GPUs, and it takes a long time, because I guess they found it useful to encode things into the latent space and just use it, even though that latent space had nothing to do with the original. I mean, it was still pre-trained on images, which you could argue
Sure.
maybe is similar, but I guess, yeah, I had to change my opinion about the usefulness of autoencoders, I guess.
So Rob, this is the world's shortest autoencoder. It's actually from the Lightning site. And this is the whole thing. That's it. The entire thing.
That.
So yeah, so what this is Lightning. And so you just say, I'm going to implement a Lightning model, and this is the forward pass. And so in this pass, I'm going to encode. This is the training step. So I'm going to resize the data. I'm going to encode the data into this latent vector. I'm then going to decode that back into this other vector, which should be the same as this one. I'll then compare the difference between the generated one and the other one. And that's my loss. And you're done. That's it. This actually works. I can run it and it will train an autoencoder. So I thought that's an achievement. That is really quite amazing that you can do that in that amount of code. That is remarkable. So, I'm sure you're not feeling great.
This is the best I felt in days, trust me.
Okay. Okay, and so then I'll show you this one, which I think is no, that's the self-attention one. That's not the one. What did I call it? I put it in the GitHub. I can't remember. Do you remember what I called it? Sorry.
I can't remember. It had liquidity, I think, in the name.
Liquidity classifier, was that it? Right. Yes. Okay, so let me explain, Rob. I'll walk you through this. So I took that previous autoencoder example I just showed you, and I modified it to work on your data set. So I load the data set. That's what I do here. So that's me loading all of the data in that spreadsheet. And then what I'm doing is I'm encoding the data into a fixed size, set of fixed size latent vectors. So that's the encoder. I'll come back to that. So what I did is I didn't know which columns to pick. So I just randomly picked 28 of them. But I excluded some of them. I excluded these ones because I don't think it made sense for them to participate in the test. So MNIST is 28 by 28 images, so 28 pixels by 28 pixels. And so what I said I would do is I would take 28 columns and I would take 28 continuous time steps across the 28 columns. And I'm going to draw that as a picture. So when you draw the pictures in MNIST, you get this. And these are the pictures you get when you just do exactly what I just said, where you just randomly sample 28 columns and you randomly sample, and from that you randomly sample a time, and then you take 28 time steps and you just draw it as a picture. And then you train the autoencoder on that. And amazingly, it converges. It actually learns something doing this. So that was surprising. I don't know what it learned, and I'm not even I can't even speculate, but this leads to a whole bunch of questions. Okay, so which columns do we think are significant? Can we just hand pick them? Are they all significant? If so, I'll use them all. That's fine. We could train across all of them. I don't think there's a problem with that. And how long a time period is long enough? Not sure.
Okay, so in general, more is better. I could certainly come up with a list of 28 that would be better than 28 selected at random.
Okay, great. I can't, which is why I randomly selected them. But there's no reason I couldn't include all of them that you think are worthy of attention, right? So I just matched the MNIST data set just because I didn't want to have 1,000 different variables changing at once. I just wanted to have something I could understand. And I think this is quite comprehensible. We can clearly see that there is a similarity between these two systems.
Interesting.
Yeah, the other thing that's going on here, and this is the amazing thing about Lightning, is you can see the network, right? So what this is saying is that currently it's just taking 28 by 28 numbers and encoding them into 128 numbers. So it's compressing this many numbers into this many through this 3-layer network. And then it's decoding that back into the original set of numbers. So I'm training the autoencoder so that it can compare its input to its output. This could be any number you like, right? So this could be 1,000. This could be 1,000. Doesn't really make any difference. And we could change this to be a convolutional network. This isn't convolutional, right? So proximity of pixels doesn't mean anything in this situation. You could just draw it as a line and it would do the same thing, right? So the squareness of it has no meaning in this context. Anyway.
All right, so how would you use this like for categorization and prediction?
Okay, that leads on to the other point I made last week, which I'll jump to next. So I came up with a measure of liquidity. Do you want to hear it? It's a very strange one.
Yeah.
A stock is liquid. One stock is more liquid than another if, given a new piece of information, that stock returns to equilibrium faster than the other stock.
Okay.
So if a piece of information comes out about Apple and 7 minutes later the stock price is stable again, and if a piece of information comes out about Joe's garage and 3 weeks later nothing's happened, I would argue that Apple is more liquid than Joe's garage.
Yeah, I guess that works.
I guess the challenge is clarifying what is a piece of information and how do you judge based on infinite number of information, which one is actually relevant. And
it's a very good question. Yes. And I'm not disputing it. Yeah.
Yeah, so it's more like a speed of convergence back to an average.
That's right. Yes.
Some conditional average.
And if we notice over time that the speed in which it returns to average is increasing, then we could say that its liquidity is increasing. And if its return to average is slower, then it's decreasing in liquidity.
Yeah, I think there are theoretical models that are kind of loosely based on that premise too.
I'm sure. I'm not claiming any of this is novel, by the way.
No, I think it's all interesting, and I don't think anyone has ever thought, at least in my area, has ever thought of these questions, David.
Okay, well, maybe we should kind of try and weave that in. How would we detect an information event? That's interesting.
Well, you got a couple dimensions. I mean, if it's real information, it's probably going to show up in prices.
Okay, so price shift.
And if it's a liquidity type of, I mean, this is sort of a standard approach. So, yeah, here's an example. You've got a stock, it's trading, and then all of a sudden there's a really large chunk of the stock that transacts.
Mm-hmm.
Okay, so generally what we see is if that's somebody wanting to buy, that's going to cause the price to jump up to essentially induce more people to sell so you can buy. And then the question is sort of what happens to the price afterwards. So there are a couple alternatives. So one is, okay, it reflects new information. I don't know, earnings takeover or something like that. And in that sense, you don't necessarily see the price fall. If it's much more idiosyncratic, then you would probably see the price jump up and then come back down. So you could kind of do the same thing on the price variable too. Sort of, you know,
so volatility in price.
Speed of convergence back to wherever. But again, I mean, like Pine was saying, you got these sort of two competing parts. So one is, yeah, there's information out there. And the second is it's just sort of idiosyncratic. So it's more, you know, it's more sort of noise based. It just happened to be that somebody decided to do something large at that time, even though they really didn't know anything.
I guess I'm not trying to predict a liquidity event. I don't know how to do that. And I'm not suggesting I even have a hypothesis as to how we could do that. I'm simply trying to have like an ongoing tick, if you will, a best estimate of the liquidity of each of the individual stocks.
Yeah, so I'll have to dig up the models, but there are some measures that people have proposed to try and get at what you're describing.
Cool.
Now, I don't, yeah, let me just, yeah, I'll dig them up.
Okay.
But yeah, keep going.
Well, that was it. I mean, that was last week. I'm just trying to bring you up to speed. So you're asking about how do we use autoencoders? And that's a very good question. So here's a hypothesis, and we can all shoot this to pieces, and let's do that. So if I have trained an autoencoder, then small changes in the latent vector should produce similar results, both in terms of, okay, let me describe it this way. Make a small change to the latent vector and see how big an effect, or essentially use the encoder to judge whether it believes that that change was significant or not. So if I have a latent vector and the discriminator correctly detects that this was synthetic data and not real data, and then I essentially add a small amount of noise to the latent vector, and then ask the ask the discriminator again. If the discriminator starts thinking that it changes its classification of the latent vector based on small changes, then we might be able to determine the underlying beliefs of the encoder. That's one possibility. The other thing we could do is we could once again add noise to the latent vector to generate counterfactuals that are nearby the current situation. So I guess what I'm trying to get at is volatility. If we make small changes to the latent vector and the generator generates wildly different outputs, and the discriminator starts, becoming confused as to whether it's real or not, then I would argue that that part of latent space is very unstable. It's not flat. But if we can jitter the latent vector and everything remains stable, then we can basically say that that part of latent space is smooth. And so then if we take real world data and we feed it in, and then we add noise to the real world data and the system is very volatile, we could make the assessment that the market is very volatile and that small changes are going to have big effects. So we could use this as a means of measuring volatility, or beta, I think it's called, in the beta in the market, just by essentially training an autoencoder on the financial data, adding noise to the latent vector, and then seeing how stable the encoder decoder are with that new latent number, that new latent vector in the middle. So does that make any sense, Pine?
I'm trying to understand where this generator discriminator comes in, because autoencoder is not a generative model, so there is no generator or discriminator in an autoencoder. So how do you connect this to the
encoder decoder?
They're not generative models. You can't generate new samples from an autoencoder.
Sure, I can. I can take this number Z here, and I can encode it, and then I can add noise.
Yeah, but you can do that to the data we have now too. It makes no difference. Like, it's not going to get you anything more. You won't be able to control any generation in any way. I mean, you can take the data from the tables and add noise to it, and that's equivalent to what you're doing here.
Really interesting. So because I would have thought there would be non-linearities.
Well, there will be, but you have no idea what those are. I mean, that's why I suggested if you wanted
to go to the variational autoencoders.
Yeah, so that's a generative model. So sure. Yeah, so I think.
Okay, and I haven't done that. Sorry, you're right, and I'm not disagreeing with you that we should make that step, and I agree.
I mean, you can try it. I just don't know how to. So the encoder gives you, let's say, a vector. I think in this case, I don't know what the size is. Whatever.
128.
128. Okay, so you get 128 numbers. So what is the plan? You just want to jiggle those a little bit, and
Right.
then the output will be different. And then what? How do you judge anything about the output or the input? Like I feel like there's no information to go on based on some mapping between the input and the
Right,
output.
because we haven't trained it as a GAN. You are correct. Okay, fair comment. I'm mixing metaphors. So yes, fair comment. Okay, let me think about that. I'll look at the variational auto encoders. I didn't do that this week. We'll try and get to that next week.
Yeah, I'm sure there is a version of it for Lightning too, which is just it's probably a little bit longer than this, but not much.
Yeah. So, what about multiple attention heads? So, well, first of all, I just have a question on aliasing. So in computer graphics, aliasing is a huge problem because you sample at a regular interval. You get all sorts of noise introduced just by the sampling, right? Because and it produces horrific artifacts, and that's what the whole Nyquist frequency thing is. And you have to kind of halve the frequency and do all these dance around and do all this stuff, which machine learning fails to do utterly, as far as I can tell. Doesn't do it anywhere. So machine learning seems completely unperturbed by aliasing, but surely it's a fact in time series data. No, I mean, have you heard the sparsity argument? So the sparsity argument goes that you'll actually get more information with fewer samples if the samples are truly random in their sampling and you're not sampling on a grid. That's been known for decades, if not hundreds of years.
Yeah, that makes a lot of sense. But I guess aliasing is more of a problem if you have like a super regular pattern, right? Like a sinusoid or something, and you're undersampling, then you can get weird artifacts like a line instead of the actual. But in like financial data, I guess we don't expect to see anything that regular, right?
Well, okay, so can we backtrack? So by aliasing, the way I remember it, it was like if you had two sine patterns and one of them was like a multiple of the other, like, a factor of 2, so that if you knew where you were based on one of those signals, that would tell you where you were on the other signal.
I don't think you even need 2 signals. You can have aliasing with just 1 signal if you don't have enough samples, right?
If I'm trying to sample a 10 Hertz cycle, and I'm sampling at 1 sample per second, okay, I am not going to be able to reconstruct the underlying signal because my sample rate is too low. Yeah. So,
yes. Yeah, so if your signal is the top one, but you only have very few samples, you might feel like you have actually detected that very low frequency signal, so get it completely wrong because you're regularly missing some of the information from a periodic signal.
I mean, there's probably very good material on the internet that explains this, Rob. I've been dealing with aliasing since I was 15, so it's not something I can easily.
So from your perspective, then it's really one of sort of, if you got a high frequency oscillation and you're trying to measure it with sort of low frequency.
You have to know that the regular sampling rate is in essence a low pass filter, right? It's literally rejecting all the high frequencies above that.
A simple example could be, let's say you want to predict prices or something, and let's say price of something gradually increases over the course of the week. It's always maximum on Friday and then it drops. But you're only looking at data from Friday, so you don't see any of that. So as far as you're concerned, you're missing the entire pattern. You're just seeing that the price on the Fridays is roughly constant or something like that.
Mhm.
So what are you suggesting, David, about aliasing? Like, are you saying?
Well, I
you
was
need to-
thinking of trying to do multi-head attention on a logarithmic timescale. So basically, when I'm constructing my vector of time samples, rather than sampling just 28 sequential numbers, I was thinking that I might use a non-linear sampling where I sample 1 second, 3 seconds, 7 seconds, 17 seconds, 33 seconds, and some other thing. I was thinking of prime numbers just because I have fewer modes, and we can. But then you're getting long-range information impinging on the. So basically, you're giving the system a non-linear memory. It doesn't remember things in linear time. It kind of remembers things in exponential time, right? So we remember 50 years ago, 10 years ago, last year, last month, last week, and today, rather than 5 minutes ago, 10 minutes ago, 15 minutes ago. Is there any benefit to doing that? Is there any prior that you're familiar with on this? Or?
Yeah, I mean, it sounds like an interesting idea. I mean, well, is this helping with alias? I mean, in general, I think it's an interesting idea for different reasons, but for aliasing, as long as your sampling rates are the same in your multiple head attention and is fast enough, then it shouldn't matter, right?
Theoretically, yeah. I was just wondering. I'm just
But it might
wondering
be
about time
interesting, like-
sampling schemes.
Yeah, I mean, it sounds interesting I've never seen anybody using log scale for sampling in time, but it makes sense, I guess, if you want to weigh more equally the distant pass with the immediate pass.
Basically, I was thinking of giving different attention heads different time horizons and different time kind of functions, if you will.
But different time horizons you can give by just giving longer samples into the past but you want to keep the number of samples the same, I guess that's the idea.
I don't know. I'm once again, I'm just kicking the cat here. I really don't know.
Yeah.
So I'm open to suggestion. Whenever I see regular time samples, I kind of say, okay, I should be running a filter on this, and I should be filtering out the sampling stuff, and doing a Fourier transform or something equivalent to a Fourier transform, so that I can use this as a low pass filter, because really I only have the low frequency information, and all the high frequency information is being essentially masked by the aliasing, so that kind of stuff. But that seems very heavy. I was wondering if I could do a cheap and cheerful kind of try and avoid the aliasing problem by scale jumping or using nonlinear scale. I don't know.
Yeah, I mean, I guess bottom line is that depending on your sampling rate, as you know, you're not going to get certain frequencies. It doesn't matter what trick you use, right? You're limited by half the sampling frequency, right?
Right, but true. But imagine a day trader and a historian, right? And you show them the same information. They're going to have a different view, right? They're going to attend to different things, because a historian is going to look off in the deep past and say, this has happened 30 years ago, or 300 or 3,000 years ago. And the day trader said, oh my goodness, that hasn't sold since 10, and it's now 10:04. What's going on? So they have very different time horizons and very different attention spans. I was just wondering if we could somehow encode that kind of time differential into a multi-head attention model, or some kind of a multi-agent model, where each of the agents can essentially weigh in at the end and affect your decision.
Yeah, I would think so. But it's gonna, I think it's a worthwhile.
So I don't think the historian's right, and I don't think the day trader's right. I think they're both right, if you will. It's just how do we?
A different lens that they look at the data with.
Yeah, and the beauty of these multi-head attention models is that they squeeze all of these different critics into one latent vector. So there's only one world that we live in. There's only one stock price for Apple. There's not 1,000 different stock prices, and there are millions of people who buy and sell Apple. So there's this convergence, right, where you have all these different attending agents, but there's a bottleneck in that there's only one price, right? So this bottlenecking that goes on in this multi-headed attention encoder has to be squeezed through the latent space, and then the generator generates all sorts of interesting outcomes from that. But essentially there's this kind of narrowing down to the funneling down to the stock price, which is this kind of latent value.
Yeah, but that's actually interesting. So I'm wondering how you feel. So let's say the price of Apple today. So obviously the entire history of universe has culminated in the stock price being this, what it is today. And in principle, you can go back to the Big Bang and maybe do the entire calculation at different scales and get to this price, maybe. But I guess so that's one view. And but then the question is, if you wanted to predict like today's price, how far back do you need to go to be able to do that? And is there a reasonable answer? But I guess you said you don't want to predict things, so I'm confused.
I'm trying to, well, I don't, okay, so every book I've read on this says, and if you, I would highly recommend, and I've just reread it for the 4th time, I think, a wonderful book that Rob suggested to me called Against the Gods, which is basically the history of risk. Again and again and again and again and again, they say the future is not a function of the past. Using past events to make accurate predictions of the future is, it'll help, but
it obviously works to some extent.
It.
But it works to a large extent, right? I mean, it's not perfect, but it works really well, right? Otherwise, there would be no insurance
but they just
companies.
Say, don't bet the farm on it. Don't tell an algorithm to do this without, because you'll just go broke, right? You'll end up going broke because you start to believe that the past is the true and accurate description of the future, and then you put all your faith in your algorithm, and so you tell your algorithm to start buying and selling all by itself, and then it works for a while and then it just goes horribly wrong.
But it's interesting, fundamentally, are we arguing that the future is not a function of the past? I think the question is, do we have the right features in our model?
Merely a function of the past is the way they put it.
But where is the rest of it? The rest of it is just our ignorance of the past. It's not magic, right? Unless you think it's coming from the God or something. It has to be coming from the past, right?
Well, the finance answer to that is, as soon as you think you know what the model is, something's going to change and it's not going to work anymore.
Yeah, that I get. Yes, our ignorance about the model, the true model, that maybe it's fundamental and you can never minimize it to zero. But assuming that you have all the information, everything is there. It's just a matter of, I guess that's why people compete, right? They think they're smarter than everybody else and they can get closer to the real model, even if it's changing constantly.
Yeah, or, they don't have it right, but they got it better.
Yeah,
or they
I think that's all you need to do, right?
Or they have a unique prior, or they bought special information or something. Yeah. And often they're right. So once again, I'm not trying to throw out the economic system, not at all. It works very well.
So I want to read that book, but so is that what they argue, that the future is not a function of the past? Is that the argument? That just categorically sounds wrong to me, but I guess there's a lot of context.
The way he puts it in the final chapter is that it's nearly.
Okay.
It's nearly. It's a really good model that's nearly right sometimes, most of the time, but not always.
But that's a separate question, how the model is performing or what model is good. But just fundamentally, like the future is 100% a function of the past, isn't it? Like we might not ever get to that model. That's which is fair, but
that'd be a good question for Roger Penrose if he answered emails. But
I'm waiting for my answer still.
Yeah, I mean, another way to kind of characterize it in finance is to say properly anticipated prices fluctuate randomly. So in other words, we kind of have the best model, and whatever is going to happen is going to be some deviation from what we expected.
Yeah, there's a description of
The
this.
model might not be very good.
So there's two kinds of chaos, right? There's a kind of observer independent chaos, and then there's the observer dependent chaos, where the simple act of observation has such a profound effect on the system that it actually affects the next time step, right? So
does that happen in the world besides quantum mechanics, or do we have observer dependent chaos in like finance?
Sure, the stock market. Oh, Apple's going up, buy.
Oh, that's what you mean. Okay, I understand. Okay.
Yeah. Right, as opposed to, oh, Apple went up, I'll do nothing. Oh, it went down again, I'll do nothing, right? That's very different. Right, because you have this very, very powerful positive feedback effect, and you also suffer from, what is it? They have a term for it in chaos theory, where small differences have big outcomes. I can't remember the exact.
But that is chaos, right?
Yeah, yeah. So the system is chaotic. So to answer your question, is the future a function of the past? You can never have enough information to be able to make the accurate prediction, because, you know, an electron falling into a star in Alpha Centauri will change the stock price of Apple tomorrow because of chaos theory kind of thing.
So is that accepted, that financial market is chaotic? Because just because everything is observer dependent doesn't mean it's chaotic, right?
It's not controlled, right? Every agent has agency. Like, I can sell all my stock and that can have a profound effect.
Yeah, but chaos has a specific meaning, that it's the sensitivity to initial condition. It has nothing to do with agency or any of that stuff. Like, at least in mathematics, I don't know. In the colloquial term, yeah, it's all chaotic and complex. I understand that, but if you want to go by the definition of chaos, is that if you tweak some little thing, eventually you get very different results.
And so that's exactly, and that's what I was curious about with jiggling the latent vector. Like, is the latent vector chaotic or is it stable?
Well, it can't possibly be chaotic, I guess. Oh, I guess no, it could be. Yeah, I don't know. Yeah, good point. But that has nothing to do with the world. It has to do with your autoencoder model, I guess.
The priors of the agent, which is the other. Oh, yes. Yeah.
I mean, it's just a matrix, right? I mean, the question is, you're asking, if I jiggle one of the numbers in an array, is the output going to suddenly be different? And I think it's just a nonlinear function, right? So it's a question of what is your function and whether that's chaotic or not.
Right. And so I'm essentially trying to assess, by jiggling the latent space, I'm trying to assess whether the latent space in this particular region, which is indexed by the latent vector, which is a set of values. So at position 1, 2, 3, am I standing on the edge of a cliff, or am I standing in the middle of a desert? Right. So if I'm standing on the edge of a cliff and I go, then I'll fall off the cliff and there'll be a big change. If I'm standing in a desert, I can walk for miles in any direction and nothing will change. So we can, basically, I'm suggesting that our priors might indicate, even if when we feed the numbers in of today's stock prices and we feed that into the autoencoder, and the autoencoder gives us stable results in that, you know, at 9:01, these were the stock prices, and it's predicting at 9:02, these will be the stock prices based on the autoencoder, let's say. That's only one sample. And what I'm suggesting is that you should sample nearby, like you should basically add some noise either to the input or to the latent vector, and then pass it through the system and see if you start getting wildly different results, because then you're in a chaotic situation and the system is very volatile and your risk exposure is high.
But that's still all fine, right? I mean, even for like fully chaotic, like even theoretically chaotic system, you can predict up to a certain time window, right? And I guess maybe the question is, if your goal is to predict something, you need to figure out what is that time window that even for a chaotic system, you can predict into the near future.
I see. So if it is unstable, then you would back off on the time step and take smaller steps and try and, yeah, that's a good idea. And if I'm on a desert, then I'd want to jump further and further to try and find the edge. Yeah.
Yeah, there's even a name for it. I can't remember. Some horizon. Hold on. There is a, yeah, so for, I mean, obviously we don't have dynamical models that you can study theoretically, but for like simple dynamical model, there is a horizon of predictability, where in principle you can predict, and then beyond it you can't, because it's chaotic. But every system has that horizon. I guess if you're smart enough to find, or if you're knowledgeable enough to find the horizon for your system, then at least you know when you can trust your model and when you can't.
Right. And so that's as far as I think I'm willing to go at this time, which is that, you know, this stock's liquidity is increasing. I feel confident that you can make that claim, because that's a statement about the past. You're not making a prediction. You're simply saying that based on the priors that I've observed, my intuition is, or my understanding is that this stock price is becoming more volatile, right, or less volatile. I think that that's a valid claim that you could make, right? So you could have a volatility index for each of the individual stocks.
Right. This is a great article I shared. It's called Lyapunov time. So that's the time. And somehow in this particular, I mean, it's obviously not as complicated as a financial markets, but if you go down to training computers to tame chaos, they thought that they could only predict up until whatever 6 or 7 Lyapunov time. But with these models, they could actually go a lot higher, a lot longer, and they still don't understand how. So you can see how far they could predict before and how far they could predict with like machine learning models.
Wow.
So you would wonder if you can do something like this with like finance, right?
I haven't read it, but it looks super interesting. I will read it. Thank you, Payam.
I mean, this is kind of old now, like a couple of years old, but I wonder what has happened since, I guess, this article came out. But
I'll have to read the article, but that's great. Okay, so what should we do in the coming week? Rob, you're obviously down for the count, so I won't put any pressure on you. Payam, what would you suggest I do? I'll definitely look at the VAE, and I'll try and train a VAE on Rob's data set. Let's try that. Rob, should I just increase it? Could I, my one mild request for you would be just send me a note with the columns that you think aren't interesting, basically.
Well, a lot of them are kind of duplicates. That's really what's going on in the data.
So that has a statistical impact, I believe, that if you, does it?
Well, so I mean, what would be helpful? Would you like a list of X variables that are, you know, somewhat different?
What do you suggest? I have no intuition here. I'm sorry.
Yeah, I mean, why not just start with PCA and just get whatever 2 or 3 or 5 columns that explain most of the variance and just go with that? I mean, is there any reason we shouldn't do that?
I don't know. Sorry.
I mean, that, you know. So, you know, yours is set up for a 28 column vector. I mean, we could, I don't think there are 28 principal components.
I just literally pulled that number out of MNIST. It could be 1,000, it could be 5. Like that number is just a number. Like the number 28 is not significant in any sense. So.
Well, I do like the idea of, yeah, just kind of trying to do it on a subset of the principal components.
Yes.
Because that's really tractable.
So we should do that. I mean, I should be able to work out how to do a PCA on the thing, and we'll just find out which columns are the significant ones. So the other really interesting thing about autoencoders, just one last time, and I'm curious about this myself, and you showed, I can't find the article point. At one point you showed me an article about, or maybe I saw it on Twitter, I can't remember. Basically, they were crushing physics models into a 5-parameter latent space or a 6-parameter latent space, and they were able to do like a gyroscope on a bicycle wheel with a 6 degree of freedom latent space, and they were able to model fire, like a fire, with 20 latent variables. Not 200,000, 20. They were able to take a videotape of a fire, encode that into 28 variables, and then essentially decode that back into something that looked like a fire.
Yeah, it wasn't from me, but that sounds interesting. But isn't that what physics tries to do anyways? Like you get a bunch
I'm just
of
wondering, one thing you could try with an autoencoder is to give it a ridiculously small, a low dimensional latent space, like 3 variables or 10 or 2 or something. And just, I know it's ridiculous, but you know.
No, I mean, it's not ridiculous. I think it's called the information bottleneck, right? There's like a bunch of theories. It's just a matter of how much you can compress the information, right? So you can probably, even in your model, you can try squeezing the bottleneck and see at which point are you not able to reconstruct the input, right? And if it turns out that you can still reconstruct the input with 1 variable, that probably gives you a clue as to maybe your entire data can be explained with just 1 latent dimension, right?
Yeah, so running a grid search on the loss, like if we set up a reasonable kind of framework here to sample the data, it would be really interesting to just do a grid search across the size of the latent vector and just see, you know, at what point are there diminishing returns? Like, is it between 128 and 256, or is it between 2 and 4?
Yeah, you can just like plot the error as a function of the size, and if there is some kind of a step, then you know maybe that's you can do that.
Okay, that'd be really interesting. All right, so that'd be some fun things to try. Excellent.
What's happening with Rose? Is she all right? Have you heard from her?
I think she's dropped out. I could call her back in. I'm just not sure she's that interested in this particular segment. If we go back to something more philosophical, we might be able to pull her back. I just think that she went through a bit of a life change and is focusing on family and stuff. I think she had a rough COVID event with her daughter. I don't think that went well. And so I think she's kind of inwardly focused for a bit, which I completely understand.
Okay.
So I'm off at the end of October for 3 weeks. So I'll try and keep it going from Australia. But yeah, so in a few weeks, I'll be heading out and just letting you know. So, but I'll have a chat with Rose this week. I just wanted to give her some time to catch her breath and see where she's at. But I'll follow up with her and see how she's doing and what she's interested in.
Okay.
Excellent, guys. Well, great to see you all, and we'll see you again next week. I hope that things go well this week, Rob, and you're feeling better next time.
Yeah, I'm optimistic. Thanks.
Okay. Take care.
Take care.
Bye.